A very good day to Doctor. We are from Section 1, Group 10. In this video, we are going to present a flash for separating mixture Hexane and Octane. Here is our group members. Me, Qcha Singh, Aiman bin Bakri, Nur Fadila Hanim binti Fadil, and Yongfeng Yi.
So I'll be introducing about flash distillation, which is also known as equilibrium distillation. It is a process used to separate two liquid components when the liquid and vapor phases are in equilibrium. So here how it works. The mixture is heated, causing the more volatile liquid, which is the one with the lower boiling point, to vaporize first. This vapor becomes the main component in the vapor stream. Meanwhile, the less volatile liquid stays in the liquid phase and drains to the bottom of the flash drum. Flash distillation is commonly used in the petroleum industry, especially for refining crude oil into products like gasoline and diesel.
So now I will be presenting the objective of our project. So the main goal of this project is to design a flash separation system specifically for a hexane octane mixture. Now I will be explaining the objective of the project in more detail. So a flash drum is a type of separation unit commonly used in chemical engineering. It separates the component of a liquid mixture based on their differences in their volatility. In our case, we aim to separate hexane, which is more volatile, from octane, which is less volatile, through a process called flash vaporization. So to achieve this separation effectively, we need to carefully design the system under suitable operating conditions, particularly temperature, pressure, and the composition of the feed. So this kind of separation is very important in petrochemical processes, where it's essential to purify or refine hydrocarbons for further applications.
Flash distillation is a widely used technique in the petrochemical and refining industries for the separation of hydrocarbons such as hexane and octane. It enables rapid separation of components with different volatilities in a single stage process, making it cost-effective and energy efficient. Used in crude oil refineries to separate light and heavy components before further processing. Applicable in the production of gasoline, jet fuel, and lubricants.
Lastly is process optimization. By understanding how the distillation column behaves, we can determine the optimal pressure and temperature conditions needed for the most efficient separation of components. This is really important when it comes to plant design and operation, especially in industries where minimizing energy consumption is a top priority. First is to find the operating temperature by obtaining the normal boiling point of hexane and octane from table B.1, which is 341.9 K and 398.8 K respectively. Then convert the value to degrees Celsius. After that, calculate the average temperature, then we can get 97.2 degrees Celsius. So from here, we choose 80 degrees Celsius as the operating temperature because it is lower than the average normal boiling point temperature and also allowing partial vaporization of hexane and limiting octane vaporization.
Next, I will explain the way to determine the operating pressure. First, we need to find the saturated pressure by using Octane equations. We found that P1 set is 142.59 kPa and P2 set is 23.37 kPa. Next, we find the bubble point pressure and dew point pressure by using the equations stated. The bubble point pressure is 82.98 kPa and the dew point pressure is 40.16 kPa. The operating pressure is between the dew point pressure and bubble point pressure. Hence, we choose 60 kPa as the operating pressure for the system.
Now, moving on to the operating condition conclusion for our flash separation system that is calculated from the process and composition. For this analysis, we assume that the reaction mixture behaves as an ideal solution, meaning there are no deviation from Raoult's law and the activity coefficient is equal to 1. We also assume 100% separation efficiency to simplify our calculation and focus on the theoretical design. The mixture we are working on with consists of equal molar amounts of hexane and octane, each with a composition of 0.5 mol. Hexane has a boiling point of 68.75 degrees Celsius, while octane boils at 125.65 degrees Celsius. Based on these properties, we selected an operating temperature of 80 degrees Celsius and a pressure of 60 kilopascal. These conditions are to ensure that hexane, being the more volatile component, will vaporize more readily, while octane remain mostly in the liquid phase.
Next is the flush calculation part. First, we find the liquid and vapor phase mole fractions. The Rhodes law is used to find Ki, and we found that K1 is 2.38 and K2 is 0.39. Next, we use equation 13.18 to find liquid phase mole fractions, and we found that X1 is 0.31 and X2 is 0.69. Then we use equation 13.16 to find vapor phase mole fractions, and we found that Y1 is 0.73 and Y2 is 0.27.
So, to determine the moles of vapor and liquid, there's two methods. First is by using the equation 13.107 as shown. After that, rearrange the equation to find the moles of vapor for hexane. Then plug in the value where Z1 is the overall mole fraction of hexane, which is 0.5. K1 and X1 are 2.3766 and 0.3072 respectively. Then we can get the initial moles of vapor, which is 0.45591 mole.
Moving on, for the calculation method, we will be using the second method, which involves iteration to solve for the vapor fraction V using equation 13.106 that is shown here. The formula takes into account the overall composition, equilibrium constants, and phase behavior of each component in the mixture. Starting with an initial guess of V equals to 0.5, we applied the iterative method, and as shown in the table, the value of V gradually converged, and by the seventh iteration, we obtained V equals to 0.4559 mol. So once V was determined, we calculated the moles of the liquid mixture L by subtracting V from the total fit. Therefore, L is equal to 1 minus 0.4559, giving us 0.5441 mole of liquid. So this iterative approach allows us to accurately determine the vapor-liquid distribution within the flash separation system.
The PXY diagram shows the relationship between pressure and mole fraction at a fixed temperature. At 80 degrees C, which is below the average boiling point of the mixture, we can see the bubble point and dew point curves. The area between them is the two-phase region. Since hexane is more volatile, it appears more in the vapor phase, while octane stays mostly in the liquid phase. The TXY diagram shows the temperature versus composition at a fixed pressure of 60 kilopascal. Similar like PXY diagram, it also has bubble and dew point curves that help us identify the boiling and the condensation behavior of the mixture. These diagrams are important for designing the flash distillation process, as they help us understand how much of each component ends up in the liquid and vapor phases.
In conclusion, a liquid mixture with 0.5 mol hexane and 0.5 mol octane is fed into the system. The mixture is heated to 80 degrees Celsius and the operating pressure is 60 kilopascal. The other stream contains 0.46 mol vapor, which contains 0.73 mol hexane per mol and 0.27 mol octane per mol, and 0.54 mol liquid, which contains 0.31 mol hexane per mol and 0.69 mol octane per mol. Most of the hexane occur in vapor stream because the boiling point of hexane is lower than octane.
Lastly, these are our references. And that's all from us. Thank you. 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 And that's all from